talked about the product, let's get into some technical details.
With pleasure. We've been wanting to launch this product for a long time. Very clearly, it's been years that we've been working together. And then, we really wanted to provide a proper place for developers to store their data sustainably.
Had done experimentation. You had used record mechanisms to create a somewhat specialized database. I had already done some experiments with Redis back in the day. Well, there were some stakes involved. We had operational challenges. We couldn't afford to launch it too quickly. The aim of launching a service is indeed to be able to operate it.
But also to create a team.
And to create a team. Here we are today. It's finally happening, and we're launching our first product, Cleverler. In the previous video, we talked about Redis compatibility, but we also mentioned compatibility with other protocols. In particular, we're going to open Dynamo on top of it, GraphQL, and so on. How did we create it?
This indirection at the protocol level. In fact, this indirection comes from the fact that we rewrote a database from scratch. And having rewritten this database allows us to be able to choose the protocol and to be able to expose our database in different formats, whether it is HTTP compatibility, or TCP Redis compatibility, or Dynamo compatibility. In fact, it's just a means of accessing the data.
So you can produce data via Dynamo and read it through Redis.
Exactly, it's access.
And if you want to use GraphQL, it gives you HTTP access for your mobile or web development directly.
That's the idea.
So, you're saying we created a database, so we started with some existing building blocks.
Yeah. We're not crazy. We didn't rewrite everything from scratch. You should know that when we started this project at Clever, I was all on my own with it, and we weren't going to rewrite a database. We don't have the size or the staff to do that. So, actually, that's the idea.
It's mainly that it's a really complex problem to solve. We've got experience, very advanced in distributed systems. In operational terms, we worked a lot on Apache, HBase, for example. On similar types of storage, there had been attempts to create a notion of an access layer on HBase to make it a bit more French. That said, HBase isn't exactly easy to operate. It's quite complex. It's not transactional for free either. And the challenge we had to tackle was transactionality. That's how we ensure data integrity for users.
The real key behind Materia was finding a framework to write distributed databases. And in fact, that was the whole challenge. And there is a database that meets this criterion, which is not well known. It's the kind of technology that's a bit hidden away in companies. You find it in small companies. I don't know if you've heard of Apple. Apple. I know. You can find it at Snowflake. You can find it at Datadog. But it's not something that's showcased. It's something that's a bit hidden in the infrastructure, because it's a framework for writing databases. And it's a framework for writing foundations, so it's called FoundationDB.
And to give an example, the usage at Apple, for instance, is all about CloudKit data, all the data. The metadata for photos, notes, and all the Apple applications is actually stored in that database.
Exactly. What Apple has built is a virtualization of the database. That's what they call a logical database. And so each application has its own mini logical database, multiplied by the number of Apple users. In fact, we end up with a cardinality which is immense. That is to say, we're not going to start a PostgreSQL for each Notes application, for each user. That's right, it doesn't work.
There's something special about this technology. It's not just a database framework. Tell us about the simulation. It's an industrial accident, that thing. You need to tell us it.
Sound. One of the key aspects behind Foundation is its robustness. That is to say, for those who have already operated and are on call for distributed systems, they know that production has its own life. There are failures. We can have failures, network failures, disk failures. We can lose machines. And the fact of developing a system that we call distributed is extremely complex. Because you've got timing issues, failure issues, and it's really complicated to write code that's robust and resilient. The idea behind the simulation is to provide developers with an environment that will literally torturing the database. That is to say, in the simulation, we're going to find ourselves in situations where there will be unimaginable failure cases, and that's just one round of simulation. For example, if we have two machines that restart at the same time, there's a certain probability that we'll end up reversing the hard drive, virtually. Just to say, we made a mistake, just to test it. The fact that, yes, the database is robust in fact. That we've reversed the hard drives, that it's capable of being resilient in that regard. And so, there are loads of test scenarios where we're going to command break the network, reverse the packets,
Making the clocks machines.
cut. We really imagine loads of scenarios, and, in fact, each scenario is completely different.
And what's quite exclusive is that, indeed, this simulation is deterministic. Which means that if we find a bug in one place in the simulation, we can come and fix it. The problem is replaying what we call the acid, the grain, which allows us to replay that simulation. And so to check if we've actually fixed the problem or not.
It's to solve the famous problem that when we're developing when we fix a bug in a distributed system, sometimes we're not sure we can write the unit test that validates we've actually fixed the bug. If, for example, we have a bug between two threads who walk all over each other, what is the guarantee that we won't fall back? In that case, in fact, sometimes it's really complicated to write the unit test that will make sure we've properly patched the bug and that it won't happen again. In fact, simulation allows us to say, I'm going to play an infinite number of scenarios where I'm going to have breakdowns that will intersect in completely different ways with each run.
At that point, the simulation goes well beyond just testing. We use tests on the more business-related aspects to see if we're actually correct in the implementation of what we want to implement, but in the simulation of the aspect. Right. Of the behavior of the database, we actually have this simulation that checks all of that.
This is something that is very interesting. It is that here, we are really talking about the DB Foundation simulation, which is the brick that we use. But we are currently making open source contributions to help ensure that developers using Foundation DB can include their code in the simulation. This is a first for us in the Foundation ecosystem, meaning we're the first to be able to take our Foundation applications and include them in the simulation. This is something that is allowed for us because we use a language called Rust. And we've invested in that work. That is to say that when we develop our software on top of Foundation, we benefit from the Foundation simulation.
So that means that the entirety of our database today, in everything we've developed, runs within the simulation framework and is therefore simulated. So that means that today, we're coming to the market with a technological offering that is absolutely robust, which has been tested. And the simulations we have, just to give you an idea. Every year, Foundation DB, technology, accumulating 4,000 years of operational run. This means that every year, we have 4,000 years of operational experience that helps us find bugs, and so on. So, we're looking at absolute robustness, both of the transactional engine and the storage. And we've added our development into that, so we benefit from the entirety of the simulation, across all our developments.
It also allowed us to significantly speed up development. That is to say, when A developer from the Materia team is working on a somewhat advanced feature. They are confident that they will come to validate the code under extreme conditions. That is to say, to put it simply, feedback, code review. Any pull request that modifies a low-level element of Materia will require 3 hours of validation through simulation. That is to say, it is in the process. In terms of code review, there are definitely 3 hours of simulation for any pull request that modifies the low-level hardware.
That's why I often refer to it as an industrial accident, because it doesn't exist on the market. Things that are also quite advanced. These are often research projects, but industrial application often don't exist. And there, they went on to create a language that was optimized for implementing the simulator and the development framework, only to then go and build the database. Most boxes today do the database, then try to tinker on top of it, etc. So, they really took things in the right direction, in the right order. And so, it's really quite a fabulous technology on which we can build all of this. Today, especially integrating everything we've created on top of it, we're also using Rust, so that brings us other aspects of security for the user, particularly regarding the robustness of the language and memory management.
Yes, it comes from our experience where we managed, in a past life, proxies, which was more in a world with GC, so garbage collection. So, I'm thinking of Java and Go, and we were fed up with doing tuning of the JVM and G1 with long-winded commands. It wasn't something we wanted to do. And then, when we were hitting GC issues in Go, the GC in Go can't be configured, so it's getting complicated. It was one of the prerequisites for
Don't configure. Sometimes it stops. It stops.
Sometimes it can be a bit of a pain. So, Rust was a really good tool for investing, because, in fact, behind Rust, the idea is to do the work of the garbage collector at compile time. So, in fact, we don't have runtime cost.
Another benefit we find in this technology on Foundation DB is that it also allows us to have transactional databases. What's important today? The way we deploy it, we will indeed be multi-AZ, etc. So, we're bringing resilience and distribution to the data, while being distributed in a transactional manner. Do you want to say a word about that? Yes.
It's quite incredible that an open-source database provides guarantees as strong as flagship products from the cloud universe, like Google, which offers a database that is extremely robust, called Spanner, which provides a level of transaction isolation that is incredibly strong, which is serializable. There are very few open-source databases that provide the same guarantees. And today, Foundation provides us with transaction isolation guarantees that are quite incredible.
And consequently, Materia, K.V, and the others benefit from that. And so they also provide these transactional guarantees on user data. So that means that when you've finished your transaction, on the client side, application side, and you have the guarantee that the data has been written, replicated, and distributed across multiple availability zones, and the simulation assures us that even in the event of a failure, if we've responded with OK, we can be sure that the data has been persisted.
I think that's what's important.
So, here we reach a rather exclusive level of, what could we call that? Of residue. We quite like anglicisms. Yes, sorry, it's not a big deal. It's a bit more English in the docs. What more can we say about this product?
I think we've had quite an interesting approach to database virtualization. We were talking a bit about what Apple has done with iCloud storage. In fact, we've taken the same concept, which means that with each request, Materia, we are able to open a logical database. And in fact, what happens is that when you have a request of the material type, it will be retrieved, for example, in the Redis protocol. We're going to open a transaction and, in fact, this transaction will recreate a database on the fly. That is to say, that foundation is a key value storage we created. An abstraction that allows us to simulate, to pretend to be a database. That is to say, we'll find a file architecture very similar to what you'd have in a database.
We're going to have tables.
We're going to have tables, we're going to have indexes, we're going to have a header that will give us the statuses, the quotas,
Statistics related to consumption, etc.
So actually, as we manipulate this database, it's in a single transaction. So, that's why we've really created something that is serverless, meaning the logical database only exists during use. That is to say, during the transaction, we recreate that logical database. At the end of the transaction, we commit, and it will close automatically the database.
And all of this being so virtualized that it almost allows us to have a digital and therefore ecological footprint, which is really tiny. Since, if you consume little, in terms of databases, your footprint in Materia is also incredibly negligible.
It's extremely low. Let's get started. The transaction startup figures are just impressive. We're on.
We measure in milliseconds, so what this also allows us to do is to have isolation in the multi-tenant aspect of the solution, to have encryption contexts that can be differentiated, to have bring your own key tomorrow, etc. In order to have encryption contexts per tenant. It also allows us to have operational management which is still extremely comfortable for us. That is to say that we can allow a user, a tenant, to be moved from one cluster to another because we have an abstraction above all that, and that in the same transaction we will be able to do the placement management. Users, and in some cases, we might have a user who says, I want to be on dedicated infrastructure. That's right, you create your account naturally, and we'll place you on a tailored infrastructure based on a specific type of use. Or I don't know what. Or a location. Or a location. Or depending on the type of use, we can imagine that there could be a storage engine that's more optimized for that particular user. Since we also have a choice in all of this, and that's a bit of our advantage as technology creators, we don't just have to put up with software. In this case, we edit it, and we have choices at every level regarding the construction of this platform.
And we also contribute to the foundation ecosystem, which allows us to, if we have a need, that we cannot address above foundation, we are able to come, discuss with the foundation maintainers and come to add features.
This is the moment when we call on the community. Since, overall, we are maintainers of the Rust driver. N. You mentioned it, but we are actually contributing to the simulator to have C bindings. And not just C++. This allows building simulation workloads in any language that can reuse bindings. C, which will really help a lot with that. A lot. On that.
Yes. We try to be quite active in the community, so we've deployed clusters that we can still consider quite large in terms of transactions and in terms of writes per second, despite the fact that we're still quite young. In the expertise DB Foundation, so we've given feedback to the community on tuning clusters. We are too much in Salesforce. We maintain the Rust binding, which is managed by the community. We are among the maintainers and contributors to the Rust binding. We're going to provide some feedback, experience on the operational side. And we also aim to contribute to all the tooling we have around the foundation. D.B. Since today, it's something which isn't advertised, and the companies that use DB Foundation, it's so hidden, in quotes, in the infrastructure, which isn't open source, not much of the entire operational universe. And so we want to invest and give back to the community that aspect, to be able to operate a cluster in A without a stick.
Let's be very clear, it's not exactly easy to operate. It's a complex infrastructure. We deploy it because it meets our uses, our needs, and our challenges. But we shouldn't sell it as the SPARS, a PostgreSQL server that we would let run.
Yes, no. It's still a distributed system to operate in production. It requires very good technical knowledge about the infrastructure, about the types of failures, how we monitor. It requires knowledge. On the other hand, I have to admit that it must be the distributed system. The most. The easiest I've operated and the most straightforward. I've got a story that's quite funny to tell. It's when we were, so we are. We have our own infrastructures. In Paris, Anne, there was a moment when one of the machines just disappeared. So, we go, oh, that's funny, we've lost a machine on the cluster. So the cluster is just replicating itself quietly. And in fact, there had been a handling error. Someone had physically yanked out a hard drive, meaning we really had an inventory mistake, and so the hard drive had literally been ripped out. I mean really ripped out. We didn't shut down the VM properly. We literally yanked the hard drive out of our cluster. And there was no failure, and there was no worry about it at all. A hard drive would have been ripped out in other systems. That we know. We would have been sure to have a bit more incident management to deal with.
A system that ends with a U are dead exception.
Yes, for example, this kind of system. We don't know them. No, we stick to a distributed system. That requires investment. In terms of time, and knowledge. But it remains. Let's say, one of the most affordable solutions, I think.
I've heard people say, but clever cloud, why do you dare to develop your database? Do you have the backbone for it, and all that? Why are you doing it, and all that? What would you want to say to them?
I'd want to reply to them that data storage is something that's extremely important. And actually, we see loads of people. I'm a developer myself. And I want a simple place to store my data easily. That's correct. That is to say, I don't want to think about a yes, so now I need to ensure replication. Is it synchronous replication? Is it synchronous replication? But then I lose performance. I don't want to be bothered with that. What I want is to develop applications. And today, on the market, there is no open source solution that allows to develop that. And I think that to make developers work easier, we need to be excellent at data management.
What I would add, well, you're right, is that actually, Clever Cloud has always been developing its software. Today. Indeed, some are saying, but you're starting to develop software, and so on. We've always done it. We've written our own cloud orchestrator, our load balancer. We quite like ShopProxy, but, in terms of dynamic resource management like we do, it's not really that well suited. We created Biscuit, which was the decentralized authorization crypto token. So, the batch of load balancers is Suzu. So, we've always had this approach of asking ourselves what technological solution we can provide in response to a challenge, and by creating the associated technology. What we had somewhat anticipated, we said about data, we've never really done it. Data is a bit like gravity in the cloud, and so on. And we thought, actually, today, we've always integrated solutions, open source solutions like PostgreSQL, MySQL, Mongo, Elastic, Redis, and Vorky tomorrow. And we said, okay. In fact, here we are going to arrive at a technology. Own. About data management, and we're likely to be seen differently. We had anticipated this, but I think we need to make people understand how much for us. Our nature. It's about developing software, not just being a cloud integrator. And that's why we're building our cloud solution. With the challenge of saying that tomorrow, on sovereign or European issues, etc., we can help provide a European software that can support businesses and developers in their solutions. Always with this mindset of seeking simplicity for developers. It's the developers who implement the complexity of the job. If a developer is happy, the work gets done faster, and so on. The flexibility we will bring to developers and the speed of execution. will speed up their work.
N. We're also benefiting from all our experience of cloud hosts, where we're integrating products like POSC, Redis, and in fact, due to the day-to-day management, the operational side. In fact, we create uses and we develop software that will precisely abstract the issues that we perceive and that our clients perceive as well,
while having the associated operational experience. Today, Materia, the technology we're using, we're pushing it to several tens of terabytes of storage. We've got hundreds of thousands of points per second on it. So we're quite confident about the scaling model as well. Yes, about scalability. And on top of that, as we mentioned, we have the concept of placement, which means that tomorrow we can distribute, in quotation marks, our tenants. I was going to say our eggs in different baskets, but our tenants, in a way that supports growth for that product. So, we're actually very excited to welcome a lot of users. So, the access strategy, since you mentioned it was via an API.
In fact, we've really tried to simplify the experience as much as possible. The idea is that we're going to connect to the console, Clever, Commander, a KV material. From that moment on, we're going to generate access keys. And that's it. That is to say, we don't have any instantiation of services, of virtual machines. We're in a completely multi-tenant infrastructure. Or it's the keys for the security keys, so the tokens that will serve as proof and allow access to the infrastructure. So the creation of a material, in quotation marks, is just crypto for token generation.
It's the use of your right token that intrinsically creates your access.
Exactly, and so we use a technology called Biscuit to take care of the token part.
So, Biscuit, we mentioned it a bit earlier, is indeed an access and authorization token. What's really interesting, through Biscuit, especially with these services, is that we're also going to enhance the experience on, for example, a protocol like Redis, because tomorrow, what we'll allow you to do is to embed prefixes in the token, and this will allow for scoping access to Redis. If we ever have, I don't know, I'm just saying anything, but a list of shops in these keys, in these key prefixes, Redis. The token, which includes a subprefix that would be, for example, prefix A, would allow you to say, actually, with this token, you only access the keys that start with A. And so, we come to recreate multi-tenancy in Redis, which natively does not support it, so that a user can have their access administrator with all their key spaces and can then slice that up by saying, now I'm creating a subtoken that I'm going to give to my user who will only access a subset of that data. So, through Biscuit, we're creating value on protocols that don't benefit from multi-tenancy or filtering criteria or anything like that.
So that's really interesting, indeed, and these are things that are going to happen soon. We're really looking forward to developing this, and we've already got some proofs of concept for this system that are working really well.
Let's talk a bit about the ORM. We haven't talked about how we do a bit of the magic between the protocol and the storage behind it. Yes. So, we talked about it, Foundation DB. It's a technology that is, so to speak, a bit hidden. So, it's not something where we're going to have a plethora of developers who know Foundation. Let's be very clear, this isn't a database you can just use like that. It's not a MongoDB, it's not a PostgreSQL, it's not that kind of thing.
It's a framework for writing databases.
Put on top of it,
it takes investment of time and energy and money to be able to develop something with Foundation. It's not something you can just use.
You could even say that Foundation is a distributed transactional engine that uses different engines behind it. Storage options that can be LSM, Bittree, or something else. And that, afterwards, is a free choice, exactly that one. But still, indeed, you have to build on top of what we've constructed.
The approach we took was to create a framework to write materials That is to say, we have recovered all the knowledge that we've learned from Apple, from our past experiences. On distributed systems, we created a framework, a library, call it what you want, which will allow us to encapsulate the operation of DB Foundation. This means that with this model, we can have developers who have little knowledge of Foundation and who will just use it. This library is for creating services on top of, which allows us to improving the speed of our internal developers, since not everyone needs to have an extremely detailed knowledge of Foundation. I'll take an example. Enough. Quite simple. Like when you have a database. You have statistics, you have the number of items in your table, the number of elements.
Index my index.
These are not things that developers want to do. Most developers don't really want to write their own indexing system. Ah, right, that makes sense. So, actually, the framework allows us to abstract that, and that can be used by developers.
Yes. And we've also completely abstracted the storage, meaning that when you start with a structure like a Redis list, we parse the protocol. Now, we've done a bit of magic there as well. I'll let you explain how we did it just after that. And so, at some point, we're going to retrieve it. A dictionary, a list, a native structure in there. Language in question. We're using Rust on our side, but the way we store it is completely abstracted from the developer.
Exactly, it's like, it's an ORM, we can call it that, it's a multi-tenant ORM, but based on Foundation.
And it starts from the internal serialization we use to remap all that into the storage engine behind it, which is really very comfortable from a comfort point of view. Developer afterwards to develop business applications. This will lead us to develop loads of other things beyond Redis. So, we talked about Dynamo, we talked about GraphQL. So, you're in the process of adding the query planner to optimize all those queries to be able to do pushdown. So, pushdown, if we take a moment to define it.
Actually, it's very simple. We've virtualized the database. In a database, when we make queries, we need to fetch some data. For example, we're looking for users aged between 18 and 25. This system generally uses indexes. And so, in fact, we are integrating this feature, being able to do a where in our logical database. You should know that, for this matter, we are making an open source contribution to a library from the Apache Foundation called Data Fusion. So, we're in the working group for index management in Data Fusion.
It's a really amazing library.
It's quite an incredible library. It's been 3 years. It started from a little project from a developer who was bored and wanted to rewrite and learn Rust. He wanted to rewrite an equivalent of Apache Calcite, which is a query engine in Java, massively used in big data. And he wanted to learn Rust and learn the internals of query engines. He wrote a book about his journey. It resulted in a library. And as Rust is excellent in terms of experience, development, runtime, and safety. The marriage. Being able to create data storage software in Rust, it works really, really well. And memory management, because in data manipulation in the sense of big data, not having garbage collection or heap management, off heap, all that, makes it super efficient. Frugal in terms of memory consumption. And on top of that, there's actually the robustness applied to all of this. So, on top of that, Data Fusion is now being used in more and more projects, whether they're databases or frameworks. Today, there are accelerators for Spark that use Data Fusion seamlessly. So, yeah, it's a project that we clearly haven't finished hearing about. It's a really beautiful project in the Rust community, and it's truly the one that kicked off this movement of empowerment. Redesign new data analysis and storage tools in Rust, and thus give a breath of fresh air to the big data ecosystem, which was very Java-oriented in the years 2010 to 2015. And really, the OLLLLLLLLLL, the fact of doing, in quotes. Starting from scratch, saying to ourselves, actually, we're going to take what works and get rid of what doesn't. And being able to revitalize the ecosystem, I find that really interesting.
If we go a bit further up the stack, we reach the first entry point of the service, which is the parsing. On the parser, we did magic.
We really did some magic. So, this is work that's literally in progress. I've got some PRS waiting for me, to be totally honest. So. We said it, in fact, we're pretending to be a protocol of being a server, Redis. So that means we have to be able to understand the Redis protocol. So, we initially relied on some open source libraries, which didn't necessarily meet our needs. So, actually, we started writing.
Well, let's be direct. We did an implementation on GNOME to create the RENY parser. It's a first version that worked really well alongside the core preview technology, with a few users who are a bit of sponsors for the solution. But indeed, today, we're moving on to version 2 of that.
That's right. Version 2 of that is to completely generate the parser. That is to say, there's a huge amount of work from the Materia team. In fact, it was a very tedious job, which involved parsing the TCP protocol, enriching it, and then passing it on to the next layer. And that is something that is extremely. It takes a huge amount of time and a massive amount of code for, let's say, a fairly low added value. So, what the team has developed, and it's really quite impressive, is that they started from the Redis spec. So, in fact, in Redis, you have a huge JSON file, which is tens of thousands of lines long, which will come and document the protocol for you. And so, what is quite magical, is that they managed to come and automatically create, from the spec, we are able to automatically generate the Rust structures and the parsing. Which means that for us, if at some point we want to add compatibility to a new keyword, we don't have to spend a week doing TCP dump. To see how it works, the Redis protocol, and to make sure there are no quirks in the protocol, because sometimes there are bits and pieces. In the Redis protocol, sometimes you can reverse certain things and it finds its way back, because he knows that. Well, it finds this, little ones, with, that, the type of, there, the final type.
Yes, because we clearly had to do this to support the different graphical tools and client libraries. To understand how they worked and what they needed. So that we have minimal support. That integrated well with Redis at the start.
So, the fact. To free ourselves from that manual aspect where you read from a buffer and retrieve the data that we're more or less interested in, we've completely ditched it. And we're able to come from the spec to auto-generate all the Rust code. I didn't bother to check how many lines of Rust code there are. It generates, but I reckon it generates quite a lot of lines, and I hope we'll be able to introduce this work a bit because I find it really interesting to start from a specification, from a protocol, and we're able to generate all the code to manage the server side.
Yes, and then, since we already have the first feedback from our users asking us to support a few extra verbs or commands,
This pulled 2-3 days to look at the systems aspect. And the command that the client wants us to implement is, to some commented, finally, like, uncomment a line.
Let's talk a bit about the differences. With a Redis, I think we need to be quite clear about the differentiation of the products. Materia, KV, it's a database that's compatible with Redis. It's not a Redis, it's not an implementation of Redis. It's not meant to be an in-memory cache. What more can we clarify to properly segment the two needs?
I think the very important aspect is, that we want to provide the best storage space for key value type data. And, in the end, Redis is just a means of access. It's a means of access to an ecosystem, and we're going to add more. What's important is that we provide data storage for key value type data, which is distributed and resilient, and on which you can that you can consume it in the way you want. That is to say, if you want, for example, to start a materialized view in your database for testing and turn it off straight away, that's not a problem for us, since, in fact, we've completely virtualized the notion of a database. So, we're very flexible with this operating model, and if you have a database, if you have a key-value use case where you're just storing a few keys and reading them from time to time, you might not want to pay for a full virtual machine or even a container 24/7. You want to be able to just pay for usage.
So, here, we're doing it for the key value. We haven't mentioned it, but we also have a Vault implementation which also solves licensing issues for companies looking to have a Vault service, and we developed it in particular for a client who is a sponsor of this solution and who needed a Vault service, and we said to him, well, listen, we can solve your problem. It can't be done via Vault because the license prohibits it, but we can develop the Vault implementation on hardware, in terms of storage. And so, indeed, we solve that. What little idea is buzzing around in your head after all that?
After all, that's after the KV part. I think a large majority of users would be thrilled to have storage that's more oriented. Table. A table, or rather something that would resemble PostgreSQL. For developers, it's an experience. I think a lot of developers would like to have a cloud service that charges them for their SQL table based on usage.
Serverless PostgreSQL.
No, it's a thing that we are attacking. And I think that the KV, in fact, in the end, it was only a first step to build the primitives. And now we can attack the right. Let's be very clear. We've already done the technical audit. We know where we need to plug in. We just need to get our hands dirty and develop it. We've got a couple of things to wrap up on the key value before we move on to that. And then we're getting started, but then we'll really get into it. So that means we're also going to have a European solution of a serverless SQL engine with pay-as-you-go pricing, etc. It's really great. And we're going to be able to participate in the PostgreSQL community in a much stronger way with contributions. So that's going to be a massive focus for us, the SQL. We're not going to stop there either, as we've got document implementation. So in terms of compatibility, Mongo, obviously. We're also going to be doing Zookeeper and etcd. All systems. The idea is that all systems that developers use have their Materia equivalent, so they can develop their applications smoothly, knowing that with etcd and Zookeeper we've modeled, we already know how to do it. We just need to get on with it. We're looking at a notion of prioritization.
What we can also send as a message to our customers or future customers, you can help us prioritize if you have issues and you want to be a consumer of some of these services. Feel free to give us that feedback so we know where we stand. On which foot to dance? From a prioritization point of view, we imagine things, but if tomorrow we have a big client who tells us, I really need that and I'll use it as soon as it's ready, that's how we developed Vault, by the way, as an API, as a cloud service. Yes, it was client feedback that told us, I need a Vault. We said, okay, I can't sell it to you because of the license, but I can implement it differently. Based on the hardware we've set up behind for data management. But yeah, it's through client feedback that we manage to develop the right solutions.
And the framework, Material, really allows us to develop any type of data storage service, which will give us a real complete range of services.
Years of R&D.
Years, yes, bit by bit.
What focuses on Materia is the ORM, you know, in the materialized sense. But those years of R&D, let's be honest, we're looking at 5 to 6 years. It's been 5 to 6 years since we did our first experiments. Today, we're going into production.
It's good.
Feels good.
I'm really happy.
Me too. I'm planning the next steps. Thank you. Thank you. Very well. I think we've covered the topic.
Do you see anything else to add? Don't hesitate to test Materia. KV. Give us your feedback on the GitHub community and then develop well.
Develop well. Thank you. See you soon.
Thank you.